Welcome to June 26th LeetCode Challenge. Count of smaller numbers after self. You're given a number, you're given an integer array nums, and you have to return the new counts array. The counts array has a property where the count at I is the number of smallest elements to the right of nums I. So say we're given this array here nums. So you want to know, we want to give the counts array where the numbers after 5 is less than it. So it would be 2 and 1. So you return 2 here. What number is less than 2 after to the right? It will be 1. So we have one of those. It will be 1. And what number is smaller than to the right of 6? That will be 1. And 1, there's only one of it. So there's 1. And then 1, it can't be smaller than itself. So return 0. If there's a negative, return 0. And if the element of I nums is equal to itself, then return 0, because there's nothing that it can't be smaller than itself. All right. So how are we going to approach this question? There's a couple of ways we could do this. I've seen some technique to use a merge sort or binary search tree. I'm just gonna do a double-ended queue. So I'm going to make a variable called list. List equals double-ended queue. So for each item in the range of length of nums minus 1, we're going to reverse take it from at the end and go by -1 steps. So we're gonna make a variable val be assigned to nums at element I. Items, actually. All right. So we're cycling through our list of nums here in reverse order, -1, and we're taking decrement steps from the end of length nums. Let's see. And then for each of the items of nums, we're going to make it assigned to val. So what do we want to do with this val? So if not list, if so, or so if the double-ended queue is not empty, actually I should probably make this a little bit better, because D, if not in the Deque, or if val is greater than the Deque at length of Deque -1. So under these two conditions, if the Deque is not empty and the val or the val is greater than the Deque at the index at length -1, then what we want to do is we want to reassign nums at the item equal to 0. If not Deque, else length of the Deque. So let's turn the operator there. So we want to assign, so if the Deque is not empty, we assign item at nums equal to 0. Else we make it equal to length of the Deque. So then we want to do Deque.append. Now we want to add our item val. Else, what do you want to do? So let's define a couple of variables. I, j equals 0, and the length of D -1, while I is less than or equal to j. So this is kind of similar to merge sort here. We're going to do a modified version of it. Well, not really, but we do what's called mid equals I plus j minus I divided by 2. So if the deck at the midpoint is less than the value, then we want to update I to be the midpoint plus 1. However, if the deck at the midpoint is greater or equal to val, then we want j to be updated to midpoint plus 1, minus 1, I should say. Then we want to got a colon there, and that means all this is tabbed. And then at the end of this, you want nums at the element, item I mean, to be equal to I. Then we want deck to be inserted, I val. And what do we want to do? Oh, we want to return our nums. Let's see. Item. Okay, seems to be working. Whew, that was close. So what we did here was that it works. So we have a time complexity I believe of big O of n squared, I believe, or something bigger than that, because yes, n squared, yeah, for the for loop here, and then we have an if statement, so a couple of ifs, and we have a while loop as well. I'm not actually sure in terms of the space complexity, but what we did was that we space complexity is actually a big O of n, because we store everything in a deck here, so that this is n would be the size of nums. So we instead of doing like a special fancy merge sort or binary insertion tree, what we did is we developed a double-ended queue, and then we're gonna store those items. And if the item to the right of the value is less than, it's greater than, less than the value that we're at, and then we're gonna store that into the deck here. And that's pretty much it. And we did something similar to a merge sort type of algorithm here, where we used the mid value. So this is one way of solving it. I'll show you another fancy way of doing it. It's using let's see if this works. So we're gonna have something called, we're gonna have a sorted list. So sorted list equal to sorted list. So this time we're using a built-in function here. A method. We're gonna call a variable called smaller. So these are gonna hold the value that's smaller than the value that we're at. And for num in nums, or for, I was gonna say, let's be consistent for item, for item in nums. What I want to do is that so we're gonna actually do a reversed num, sort in reverse order like we did before. So we're gonna do smaller dot append, so we want to add it if for each item. We're gonna add it using adding our sorted list here. Dot bisect left. Left at num. No, at item. Then we do sorted list dot add num item. Then we want to return a smaller number array. Going in reverse. Alright, let's see if this works. Alright, we have to let's see if this works. Sorted containers. Alright, let's pull out the big guns here. We have to import it, maybe, from sorted containers. Import sorted list. Alright, that seems to be working. Submit that. Alright, that works as well, and that'll give you a big O of n log n times. We're looping through each element in nums, that's n times, and we want to return the log n. I mean, we have also a log n value because it's recursively calling. I mean, it's not recursive. It's consistently building the smaller array log n times. Space complexity, big O of n, because we have a sorted list storing. We have to store at max n numbers. All right, that's it for now. All right, have a good day.